Okay.
And then I will share this
Continue.
screen and then bring this up. Okay, it's too bad we can't stop recording too, but here we go. All right, so this is our last session today. I'm Deanna Brasich, and I'm with Jen Carter from Vernon, and I'm from Souk. And this is our last of the 3 sessions about assessing with intention. And today we're going to focus on adding and subtracting. And there we go. And before we get going, I'd like to acknowledge that we are on unceded Indigenous land and that we are living and working and playing on this land. And we'd like to thank all of the Indigenous people of BC for allowing us to do so. Okay, go ahead.
Okay. So I'm going to start off our session here with a story that sort of connects with our past sessions on counting and partitioning. The story is called James's Spider, and it comes from the First Steps in Math training and resources. One of the researchers was kind of using their grandson as a bit of a case study. He was drawing a picture of a spider, and she asked him, how many legs does your spider have? And so he counted 1, 2, 3, 4 on the right side, and he counted 1, 2, 3, 4 on the left side. And she said, so how many legs does the spider have altogether? And he responded with 4, because he was thinking about the right side. And she said, well, what if we pulled the legs off of the one side and stuck them on the other side? How many legs would there be now? And he kind of looked at her in dismay and thought a little bit and said, well, there would be 8. And the point of the story from the First Steps in Math research and work that they did there was that kids often do not see that we can put 2 quantities together. So he could see 4 on one side, 4 on the other side, but he couldn't imagine that combination of the 2. And so it's just kind of a it's a connection to the counting piece, the partitioning piece. Partitioning is opposite. We're often having kids break numbers apart. But the point of this is that sometimes kids don't see that combination of quantity can happen. And so we need to prompt that, or maybe even model that for them. We want to, in the session, kind of talk about the difference between the meaning of operations versus computations. I know in the primary years that we do spend a lot of time on computations. Our curriculum, wants our students to understand the meaning of operations, but we often quickly jump to, can they add? Can they partition? Can they write number sentences? And we need to pay attention to the difference between these two and make sure that we are, in our teaching, making sure that the understandings of both are in place, and especially the understanding of operations. So when we think about operations, that means that we understand the meaning, use, and connections between addition, multiplication, subtraction, and division. And then computations is the part where we choose and use a repertoire of mental, paper, and calculator strategies for each operation, meeting needed levels of accuracy and judging the reasonableness of results. I think that's probably where we spend more of our time, rather than understanding what the operations actually mean.
Yes, and that spending more time on the operations will greatly affect their entire career with math. They need to know when to use adding and when to use subtraction. So it's a good point to differentiate those two for sure.
So when we understand operations, that helps us or the student know what to do, which operation to use. And then the computation is how to carry out the calculation. We choose the operation and then compute. And this kind of reminds me of the other day I was in a grade 3-4 classroom, and I asked a student, what does that plus sign mean? And right away she said, well, it means to add. And I said, well, what does that look like when we add? So they were working on 2-digit by 2-digit addition. And I could see that she was following a bit of a procedure that she had seen either her peers or her parents or the teacher do. But there were some clear mistakes that indicated that it was just memorization without understanding. So we pulled out some base 10 blocks, and I asked her to build the two numbers. And I said, okay, so when we add, what would you do with the two models that you've just built of these two numbers? And she wasn't sure what to do. I had to prompt her to push the two quantities together to know or to figure out that when we're adding, we're combining the two, or we're moving the two together and figuring out how much all together. So that understanding of the operation was not there for her, which was very interesting, because I think if she was asked to add 2-digit by 2-digit on a vertical surface or whatever, she would have been able to follow that procedure and probably be accurate maybe 80% of the time with no understanding in place.
Absolutely. And that's one of the reasons why we love first steps, and we love any type of diagnostic that not only reveals when somebody doesn't understand a concept, but it also reveals if they are getting the right answers for the wrong reasons. And that's a perfect example, is taking someone through that. I've seen so many different things with adding 2 digits, even adding the 10s and the 1s in the same number, which is kind of blows your mind there. Like, how would they even model that?
Mm-hmm.
Okay, here's a perfect example.
All right, so I always ask my teachers to have a look at this, analyze the textbook problems, and what is actually the problem here with these textbook problems. The point here with the example on the left-hand side is that in the past, in those types of resources that we have used, we've taught students what operation to use based on how the problem is structured. And in this example, it actually tells students what to do. There's no thinking involved. So it says addition. They read the word problem. They know to put the two numbers together and add. In the cookies problem, the way that is asked, Bart ate 6 cookies and David ate 7 cookies. How many cookies did the boys eat? Is an example of where maybe teachers have said, well, when you see words that involve takeaway, then you know to use the subtraction operation. But in this example, that doesn't work for the context of the problem. And same with the problem below. James went to the deli and spent $2.45. When he got home, he had $2.55 in change. How much money did his mother give him to start with? And he chose subtraction because of that word spent. And we've actually had published resources that teach cue words that help students, whether it's helping or not, help students to decide what operation to use. And so I think we can advance to the next slide, if I remember. we want kids to think about context and the meaning and use of addition, subtraction, multiplication, division. Um, they build an understanding of operations from their knowledge of the world. And so we want them to represent stories in materials, pictures in their mind, visualizing that lead to the idea of addition and subtraction. We want them to build connections between dramatic and verbal forms of problems and that symbolic representation of them. And these two stories are really great for that. I've used both of them. The dogs on the bed, I've used in grades K1. The doorbell rang, I've used in grades 3 and up, where it's just the story is giving them a context or a situation where they can think about for instance, dogs on the bed, addition and subtraction. So what I've done with this one is given students a card with a plus sign on one side and a subtraction side on the other. And as I read the story, they hold up, is this when dogs are on the bed versus are they jumping off the bed? Is that an addition situation or a subtraction situation? In the doorbell rang, we give cards that show all 4 operations, and students can indicate what's happening based on the story, because it does go through all those different situations. And that's a really quick way to see which students have or don't have that conceptual understanding in place about the operations.
You're right. That's a great way to quickly assess who's got it and who doesn't. And they won't even know. They'll just be, I think also the power, if you're holding it up, they're also going to see other people. And that would be just that peer modeling is a great idea too.
Yeah. Have to talk about the equal sign. And actually this came up on Tuesday for me in a classroom that I was working in. This is so funny. I've seen this misconception happen from grade 3, like the other day, to all the way to grade 10, where you ask students, what does the equal sign mean? And every single time you will have students, sometimes more than half of the class, even in grade 10, say it indicates that I should give an answer. And then the part that's missing there when students say that is we need them to understand that that equal sign means balance. We need them to understand, and that's the kind of core of algebra, is that we understand that equal means we're dealing with one side and another side, and we're balancing them. So I really, and I think I'll let Deanna to speak to the examples that she's put there under each equation, but some great activities that you can do to help with this. One is a story called Equal Schmequal. We've used in elementary grades, where each of the animals in the story are a different value or number of multi-links. And through the story, you put them on the teeter-totter or the scale, and by the end of the story, they balance. Balancing act is similar. And those number balances that we often have in schools also help kids see that numbers, like one quantity or number, is the same as a combination of 2 others. And the Rec and Recs actually help with that too. I'll let you, Deanna, talk to the misconceptions that you've seen as well.
Yeah, and the balances that are up there on the middle right top there, I see a lot of teachers actually put an equal sign on that red stand so that it really emphasizes that we're doing an equals thing here. I just put some examples. I asked my grade 5 students when I put 3.4 equals 7 up on the board, I said, what does this mean? And I pointed to the equal sign. Of course, they said that's the equal sign. I'm like, yeah, but what does that mean? And so those are the answers I got. They're the traditional answers you'll get. And like Jen said, you'll get them all the way up into the higher grades. So the equals tells you where the answer is. I thought that was interesting that it was actually about place. the question's finished, tells you to put two things together to get the answer. So when I put 7 equals 3 plus 4, and I had written down these definitions, I said, well, do these work now? Does that definition of an equal sign work in this area? And so through doing that and showing them the opposite way of putting the equal sign first, I got them to, I just noticed a typo. I hate that. An equivalent is such a teacher thing. If equivalent to 7, or that it was same as, and eventually getting to that both sides are equal. And I love that they had that aha moment all the way when they're 11 years old. It's crazy.
Nice. So when our students understand operations, they choose to use numbers and symbols to solve a problem rather than having to think about manipulating the material itself. You can flip on to the next one. Students should first learn to write number sentences that match how they actually solve the problem. So thinking about the semantic structure of the situation, even though this may produce a non-standard number sentence. So we want to encourage them to think about what is actually happening in a situation. If it's an amount first, write that down. And then if there's an action, what operation represents that action? And then are there other quantities that result? So we want them to practice writing it down as they think about a situation.
Absolutely. So I think we all push for that 3 plus 4 equals 7. We like to see that on their papers and their whiteboards, but trying to get them to go, what? Like even a question mark or a little happy face plus 7 equals 11. That's what we're meeting here, is try to match the actual meaning to the sentence that they write.
Yeah. And young students should, and just what you said about variables, young students should be taught to use representations that match the modeling of counting process they have used. So 3 plus what equals 5, that question mark could show that. And we can talk about it being a variable and that kind of piece of that missing piece that we don't know.
Yes, I always call it mystery number, no matter if you're using the algebraic X or using a box, but just mystery number.
Okay, and I've heard Annie Fetter talk about this, but also Brian Bouchard is a great resource for this, but it's helpful when we have students who have been trained to look for keywords that tell them what operation to use. It's helpful to take the numbers away from the problems and just give the situation, and then let them think about what operation might be involved and what numbers could also make sense in that situation. And so we've added a link here to Brian Bouchard's blog and great resource of numberless word problems that you could use in your classroom to help students just have that experience of really just thinking about a context without numbers, without the cue words that kind of flag an operation with those numbers, and let students kind of do that thinking and that work.
And the kids really love this because it's so different. It's novelty for them. And when you show them these problems without any numbers, they're kind of freaking out a bit, but it really does bring about their understanding of operations very quickly, especially if they are in older grades and they haven't been exposed to it at all. Okay.
Is this to you now, I think?
Oh, no, it's you, I think. Yes, it's you, but we could both do it. It doesn't matter.
Oh, okay. I can remember. It's been a couple days. So we wanted to talk about the phases of how, like, basic facts. This comes up actually with the teachers that I work with very often. You're right, this is my slide. I remember this now. Cuisinart rods threw me off. I get a lot of questions about how often do we have kids practicing basic facts? Should it be automatic? That type of thing. And we do know that we want, and our secondary teachers really appreciate if kids are fluent with basic facts, but not in a way where there is a lack of understanding. We want that number sense in place. We want kids to know what those operations mean, and we want them to be flexibly and fluently moving, that like playing with numbers to help them understand and quickly know what the basic facts are. And this actually does happen in a bit of a continuum. There's actually a couple different little continuums that happen when kids are developing their basic facts. I did a bit of research on this because like I say, in my district, I had a lot of teachers asking about this. And the first most important thing that I think I read about was that it does need to begin with counting. Kids need to have that one-to-one correspondence. They need to be counting on their fingers. Joe Bowler talks about the importance of kids using their fingers and matching one-to-one the number words that they're saying with the quantity that it represents. And then we don't want kids to stay with counting forever. We want to help them move on to, okay, you've counted 5, now you have 6 more. We don't need to start at 1 again. We know there's 5. We want to trust that we've counted 5, and we're going to add 6 more on. So we're going to start with 5 and count 6, 7, 8, 9, 10, 11, whatever that we're adding on. That's a really important next phase. Also, we don't want kids to hang out there too long. Once we know that they have that understanding in place, then we want to have them start to trust, well, I know when I added 5 and 5, that was 10. I don't need to count 5 and then count 5 more on. I just know, I remember, I can see with my hands, 5 and then 5 more is 10. 5 and 5, and then 1 more is 11. And some of those derived facts that Vandewaal and Trevor Calkins and even Carol Fullerton have talked about, doubles plus 1. So some of those using what they know about the numbers that they have combined and they trust to figure out what they don't know. And then eventually that leads to that automaticity where the basic facts are memorized. We very often in the early years jump to having kids memorize, and parents do this too. And we have in the past asked kids not to use their fingers, but research has shown now that all of these stages are important for our kids to go through, but we don't want them to be there forever. The other continuum is that this is more from First Steps in Math, is around kids using actual objects and role-playing situations and using counting to solve. So we give manipulatives or counters or whatever, we have them build, like I did with the little girl the other day, and asking her to push them together. And then moving from actual manipulatives, what I was trying to do with the little girl the other day was, okay, do we have to build with the base 10 blocks every time? Could we just draw a representation of that? What does 10 look like? And talking to her about the 10 rod and helping her understand that that's 10 units that are stuck together and we can draw that as a rod. And eventually moving from the drawings then to the symbolic, where we're writing the numbers that represent those pictures or those quantities, to finally putting that into an equation. So those phases are really important to move kids through. And if you notice a student you can tell something's off, like what happened with me the other day, then you have to go way back and pull out the concrete objects and have them use their fingers and making those connections from the symbolic to actual concrete things.
Awesome. Yeah, it always makes me think of Kathy Marks Kirpan and her concept circle, and starting with objects to do
Yeah.
one more, two more, and then moving to pictures and then moving to numbers. Those are a great way.
Yeah.
Okay, this is the really crazy slide that we forgot to fix. But if you look at the top right corner, I think this is probably the most important part on this page. And that is that there are some things we want to ensure kids have before we move to adding and subtracting. First thing is being able to count forward and backward to 20. That's one thing you want to definitely assess every kid. They need to be able to count 20 objects and know that the last word tells how many. And they also need to know that how many is not going to change no matter how you move those 20 objects around. We also want them to be able to read and write the numbers from 0 to 20. But we also really quickly want them to be able to state the number before and after 20. And that's something that builds up their one more, two more facts. And you can push it as far as you can. But we want to make sure that these are all happening before before you are starting to have them explore adding, subtracting. Okay. So moving from situation to operation is just like Jen had said, that we start with a situation. So we want to give them a context, and it's a great word, that context or that situation, and keep that in mind all the time as you're exploring adding and subtracting. So when you give them that situation, they're going to start by using their bodies or using materials, and they're probably going to count up, like Jen had mentioned. Eventually, they're going to move to being able to represent their model with that number sentence. When they're comfortable with that, they will move to the same type of situation, but this time they are going to go directly with the numbers and their symbols, and being able to, again, choose the operation. Now they don't have the help of the models, but they'll eventually learn to choose the operation that they'll need, and then they'll be able to use a calculation or the number sentence to compute it. Okay. Just a little side note about subtraction, because we often think that addition, will be just the same as learning subtraction, but it is a lot more difficult for kids. It's hard for them, especially Jen had mentioned those cue words. A lot of cue words will trick them into thinking it's subtraction, where it's actually addition. And so using a varied amount, a variety of questions that bring out the operation of subtraction is really important. So for example, what's the difference between 7 and 2? I still have grade 5s that look at me like I'm thinking the appearance of the 7 and the 2. How much more is 7 than 2? What's left if I take 2 from 7? If I count back from 2, back 2 from a number line, what number will I come to, etc. So it's about ensuring that they see the subtraction in many different ways. And I have that little stop sign up there. Again, those keywords will eventually not work for them, and you're just setting them up for failure with that. So there are some addition and subtraction types, and the kids don't have to learn these labels. These are the 4. So we're going to go through them one at a time. I'm going to start with change there in the top left. This is when students have to transform a quantity by adding or taking away from it. And that's the one that we stay in quite often because it's got a nice action in it. Kids can model it with quantity or with their bodies. But we too often just stay there in the change. So for example, if you have a change type of question with joining, you have 5 bears, you'd like to have 10, how many more do you need? You still notice that it's a well-worded question, a well-worded situation, because it's not just saying 5 plus 2. And then if you have a separate question, you have some bears, you gave your other 3 of them, now you have 7 left. How many did you start with? So again, not a classic A plus B equals C question. Then we go over to combine. This is another type, and if this would be your baby step to move into, so get away from all change type ones and move to combine. And that's when you have 2 static quantities that are either separated or combined together. For example, you have 7 brown bears and 3 white bears. How many do you have in all? You have 10 bears that are bears and 7 of them are brown, the rest are white. How many are white? Again, this is something they can model, but there really isn't an action in there. The next is equalizing. So these are the two other ones that we often ignore when we're teaching. Equalizing is, again, an easier one than comparing because it actually suggests an action, and we as teachers like that and kids like that. And so students equalizing two quantities, for example, you have 10 brown bears and 7 white bears. If all the white bears take a brown bear as a partner, how many brown bears won't get a partner? And that, again, you're equalizing. They're matching them up to see how many that they'll have left over. Compare is a little bit more difficult because, once again, we're dealing with static quantities. And there is an action. We know there's an action, but it's not really apparent in the situation you give the students. For example, you have 10 white bears and some brown bears. You have 4 fewer brown bears. How many brown bears do you have? You can see why teachers would maybe stay away from that, because it would cause chaos in the classroom. But the more you do of these type of questions, the better the kids will understand what is needed when they are looking at a situational example and how to choose the operation before they even look at the numbers. So we just have a little quiz here for you. So we have the start unknown, we have a change unknown, or we have result unknown. And most older textbooks and still a lot of worksheets that we're seeing have a lot of result unknown questions. And we want to change that up and make sure we don't know. We give questions to students that have the start unknown and the change unknown as well. So just take a moment to look through these and decide whether or not it's start or change or result unknown. So Anna had 7 trading cards, and then her brother gave her 3. How many does she have now? Okay, the answer would be result unknown. So that would come after our equal sign here. Anna has 6 jelly beans, but would like to have 11. How many more does she need to get? This would be a change unknown. Then we have Anna has some marbles and her brother gave her 4. Now she has 10. How many does she have in the start? That would be start unknown. Anna has 12 trading cards. She gave her brother 3. How many does she have now? This again is our traditional question, so it's a result unknown. Again, changing it up. Now Anna has 13 jelly beans and she gave her brother some. Now she has 7. So here again, we know the result. What we don't know is the change. And last one, Anna has some candies, gave her brother 3 of them. Now she has 8. So again, the beginning part, the start of the situation is unknown, and that's why we have a start unknown type question. So very important that you are giving all these different types, and that if you're using a resource, that you look for a resource that is providing you with these different types of questions. The other thing is that needs to be spent quite a lot of time on is the equivalent number sentences. And kids need to know that we can represent the same situation with different number sentences. And by doing that, the kids will be more well versed with the inverse relationship. So they find it really difficult to work with representations that don't match the actions. So Jen had spoke about this at the very beginning. We need to ensure that students have the opportunity to write a number sentence that we see there, question mark, take away 16 equals 18. Instead, what you'll find is they're going to write 18 plus 16 equals question mark. They're going to do the inverse, but we want them to be able to do both. So giving students a situation and asking them to write both types of question is really important, and one that you want to practice every day until they get it. These are some great tools that you can use, some really quick tools that everybody really should be using. And I find that some kids will have a better understanding using one of these representations versus another. I usually start with the parts whole chart that you see at the top, but sometimes I need to move kids to more of the almost like the rec and rec model where they have 5 and 3 in that way, and they're seeing a total of 8 and using the drawing around that. Then you have the bar model, and last year I had 3 kids. That's the only way that they could understand the inverse relationship, and that we could write situations in a couple different ways. And then there's the number bond at the bottom, which works really well as well, and allows more parts and more flexibility, I find, than the parts whole. Okay, so here's some samples of Tegan's work, and this is from First Steps, and they asked her to write an equation that they would put into a calculator. And what that does is that forces a student to think of the inverse every time, because they can't put a start unknown into a calculator. So once again, calculators in the hands of our early learners can really work wonders with them. So if you look at Tegan's answers, you probably notice that she's using 7 plus 3, 7 plus 3, 7 plus 3, and all result unknown types of questions, even though this doesn't match what she should be doing in the equation. When she gets to number 4, she sees the word gave, and she switched it to 7 minus 3. This is because it's a very traditional question that we're having our kids do all the time. So that one she got quite easily. You'll notice that she's also solving she's putting the answer, she can solve it in her head, and she's putting it into the equation. And that's again why we want to make sure we use the calculator, so that that's not the focus. The focus is on what is the inverse, what would you use to solve this in a calculator. So obviously we think children find result unknown a lot more easily because that's what we're having them do all the time. That's what we're showing them. It'd be awesome if that would be the last type of number sentence that we showed them. And then why is it important? This is what I've just talked about, the fact that if you put in the calculator, it forces them to really understand the operation and to use the inverse. And lastly, making sure that we use larger numbers. So if they're able to answer the question in their head and then force that into a number sentence, you want to really up the answers, up the size of the numbers in your situation. And again, they don't need to solve this. This is just being able to understand what operation is happening. Okay, so another little test. Which number sentence would you enter into a calculator? So if Anna has 117 jelly beans, but would like to have 310, how many more does she need to get? So here they cannot write 117 plus an amount in a calculator. They need to be able to switch this around so that it's an inverse, so that the result unknown, the calculator is going to only give them a result unknown. So they need to do the inverse there. And same with this one. She has 157 jelly beans, and then now it's the change unknown. And we have the result, which is 78. Notice that the size of these numbers are a lot higher, so a lot larger, so that they are really having to figure out the inverse part. They're not just readily doing it in their head and making it work. So here we have 157 minus 78. Again, the answer is not what we're focusing on. Just like Jen with the books, we're just focusing on, am I adding, am I subtracting, and how are those numbers going to be put into the calculator? So our goal, of course, is to make sure that they see all 3 situations for students to solve, not just the result unknown, and that they do that through the continuum Jen was talking about, from the concrete to the symbolic. So here's just an opportunity, and Jen and I, when we both did the First Steps training and being able to train other people with First Steps, we found this quite difficult. And so we'd like to have you try writing one and see how you do. And would you recognize one in a resource that you were choosing? Are they providing these types of problems as well? So if this is the question where we have an unknown change, just quickly put in the chat box, don't press enter, put down a situation, write a situation that you can explain to your students. And again, when we looked at the different types of questions, are you dealing with a combine or a compare or an equalize? Because that's a way to level up your questions and have a real understanding with your kids, is to play with those types of questions in this same situation. Okay, here are some first steps ones that Jen and I love to use. These are primary ones for sure for the beginning. So we have at a party, 5 children want red jelly beans and 8 want yellow jelly beans. This is more about, can they write the number sentence for this? But the bottom part is what we really want to know. How did they work that out? And that again could be with pictures. The great thing about this is it can be differentiated. Some will use some concrete objects, some are going to use pictures, and some are just going to go directly to the symbolic and writing of the numbers. So within this one assessment, you're going to get a lot of information about your students and where they're at. And then problem B, we have at a party, some of the children wanted red jelly beans. So we're starting with a start unknown, and this is where you're going to see whether or not they're able to choose operations and compute an answer when it's not the traditional result unknown question. Here's the empty boxes, and this is what we're asking them, what are you going to put in the calculator to solve these? And before you do this assessment, you can do a lot of activities that will ask them and have them explore doing this. So they will have to really understand how to use the inverse here. You want to bring out your parts whole charts, you want to bring out your rec and recs, you want to bring out your number bonds, your bar models. Those are what's going to help the kids figure out what they're going to put in the calculator. What is their understanding here? So here's a few samples of them. And you can see that at this top one, they've figured out the answer and they've just forced it in there. They haven't followed the fact that you want something to be put into a calculator. Same with these other ones here. They've just put it in there. They haven't added 27 and 34. And this is again getting at whether or not they understand that there are equivalent number sentences. There are more than one way to write a number sentence for a situation. All the way through, we have like even this bottom one, the middle one, 17 plus mystery number equals 36. What would you put in the calculator? 17 plus 19. So they've already solved it in their head. And once again, if you find that's what's happening, then just use larger numbers so they're not able to do that. The bottom one is very interesting. And this shows you that they do not have that understanding of parts and wholes and the relationship between the parts and the wholes. So looking at this child, you would be going back quite far to rectify the situation and help guide them out of that misunderstanding. Okay, and here's just another one. How much taller? This one I really like because it says how you worked out the answer, but they've also added that extra layer at the bottom where they're asking, write a number sentence. You put in a calculator to work it out. So this just kind of pushes them a little bit higher. And you could do that with those other jelly bean ones. You could add that little aspect on the bottom and see which of your students can do that. In the First Steps resource book, you will find all of these learning activities, K to all the way to grade 8, that allow them to explore the different question types, going from concrete to symbolic, having having the start unknown, change unknown, result unknown. All of these will do all of them. And once again, in a resource, you want the resource to be providing you with those situations for your kids. So again, here's another one. So if you go into the resource book of the First Steps in Math, you will find these really helpful ones. And I had been mentioning earlier, with a colleague, that you can actually cut these out, these little strips of them, and they're a great thing to send home and say your student's struggling with, your child's struggling with this. Can you do these types of activities with them? So
And
we're gonna
actually, one thing
oh,
I'll mention about the activities in First Steps in Math, because I was part of an inquiry around the First Steps in Math diagnostics and what you do next when you see those misconceptions. It's really hard to find a game or activity or task that specifically targets that concept or misconception. Often the things you find will have a lot of other things involved, whether it's reading a problem or maybe it's solving, but a lot of operations, or, there's often a lot of other factors. And with these tasks, there's specific to that concept or that misconception. So that's what is nice about them. And it is a challenge to find things that target those things that students need.
absolutely. Great point. Okay, I think we're going to end off with this, Jen.
Oh, well, yeah, I just added this at the end because Joe Bowler has done research around what I had mentioned earlier about where we jump to memorization and that kind of like speed, fluency piece. And so this is a great read with lots of amazing resources at the end where it shows that it's important for students to understand what's going on with the math and the operations visually, and to practice that way. So I highly recommend checking this resource out. And that whole idea around speed, we want to be careful. We don't want to time kids with their basic facts. We want them to see it visually, support that mental math piece. And so this is a good resource for that.
It's a great resource because she's not saying that she doesn't want the children to be able to do them fluently and quickly. It's just the way to get there should be without fear. And so it's a wonderful article. And of course, if you don't know the U Cubed website, it's a must to go to. You'll find a lot of things. That's a whole Pro D day there, just exploring that website. Okay,
Yeah,
so that is it.
we're at the end.
We are at the end. So it's been wonderful being with all of you, and exploring all the way from the beginning of counting through subitizing, partitioning, place value, and then bringing it all to the adding and subtracting. And it's a great place to stop because adding and subtracting is not going to happen for your kids or with true understanding unless all of those things we've already talked about are in place. So I'd like to thank Jen for doing this with me.
I want to thank you too. It was
Yeah,
very fun.
it was fun. We'd like to thank the BCMT because as executive members of the BCMT, they provided the support for us to be able to do this with everyone. So now we can send everybody all 3 links again so they can peruse it and see these recordings as often as they want.
Yes.
Hey, thank
Good.
you.
All right. Bye, everyone.